develop one method, and nowadays this method is used for design of alluvial channel. In fact, Indian code also suggests this method, that is the tractive force method of design of alluvial channel. So after covering this Kennedy's and Lacey's theory of design of alluvial channel, now we'll be moving on to design of alluvial channel using tractive force method. Well, now we need to know what is basically tractive force. Well, so tractive force is the force exerted by the flowing liquid on the perimeter. Perimeter means basically why it is being written as perimeter, or why I am writing it as perimeter. Say we shouldn't say that it is the exerted by the fluid on the sediment or soil, because sometimes the perimeter may be consisting of something else, but still the flowing fluid will be exerting a force, drag force, on the side of the channel. And if sediment is there, if soil is there, if it is an unlined canal, we are talking about, of course, alluvial channel, then in alluvial channel the drag force will be exerted on the soil particle, of course. So that is called as tractive force. Now, what that force, that means when a fluid is flowing through a channel, then what is the drag force, or where from it is coming? That is basically the force that is governing the flow, or the force due to which the fluid is moving. And that is nothing but the component of gravity force acting in the direction of flow. So we can say that in uniform flow, it is equal to the component of gravity force in the direction of flow. So that is what the tractive force. But for the design purpose, or for developing the concept of design of alluvial channel by tractive force, we need to know about another term that is called unit tractive force, or so that unit tractive force is also called shear force or drag force. So unit tractive force means tractive force per unit area. When we talk about force per unit area, we use the term pressure normally, or say stress, and that's why. But in case of tractive force, we are using the term, popularly it is being used, and we are using the term that is the unit tractive force. And of course we can call, that's why this is a shear force, or say we can call it as a drag force also. Now, if we recall our earlier discussion itself in uniform flow, then we had this sort of analysis. Say in a channel, this is the bed, and then water is flowing like that, and let us consider, say, this portion. And well, let me draw, say this is the section, this is the section, and then sectional area is this area. And of course we could take we are considering uniform flow, so wherever we are taking the section, it doesn't matter. But if the channel is non-prismatic, it is better to take the section from the central part, so that it represents both sides in a well represented way. Now say this is area, and this is the perimeter. Perimeter is the side length. This is the perimeter, and the weight of this is W. Weight of this fluid is W. Okay. W means this W, if I represent this W to write the total weight, and say unit weight of the fluid, if I write as, say, small w, unit weights, sometimes we are using the term gamma also, gamma W, to represent unit weight. Well, in different book, different symbols are used. We should not get confused by these symbols. We should know the very physical meaning of this one. So it is the unit weight of water if we write. Then unit weight multiplied by the volume of this fluid. We are talking about the fluid volume between section 1 and 2. So what is this volume of the fluid? If the area is A, and if we take length of this portion L, say L, length of this portion as L, then what will be the volume of this one? It is A multiplied by length. A multiplied by length. This is what the weight. And now what is the force that is acting in the direction of flow? Well, now if I draw a perpendicular line, then this angle is theta. This angle is theta, perpendicular to the bed, because the slope is theta. If I give this angle here, this is also theta. Okay. Well, so if this is theta and if it is WA into L, then this force will be, that is, which is basically, because the flow movement is in this direction. So this force will be equal to, WAL into sine theta. WAL sine theta. Well, now, for very small value of theta, generally this canal system in agricultural field, when we design, then these are normally not having very steep slope when we talk about plain area. And then this theta, because of course this slope always remain generally small, because we are talking about this part we are doing for design of alluvial channel. And in that case, in alluvial channel, it will be normally in the river valley, and that way the slope will not be very high. But of course, if we talk about agriculture in hill somewhere there, and in that case, this soil will not be alluvial, and as such, we are not talking about design of this sort of canal. Well, that design concept will be different, because the soil will not be alluvial channel at that point. Well, so for small value of theta, what we can have, WA sine theta, this for small value of theta we can write, for say small value of theta, we can have sine theta is approximately equal to theta. And what this theta is? Theta is nothing but the bed slope S. Bed slope S. So what we can have, if this force is written as F, so what we can have, that F is equal to WAL and S. WAL and S. Well, now, this is what the tractive force as per definition. The force exerted by the flowing fluid. This is the force which is driving. So this force is taking the water. So this is the force exerted by the flowing fluid. But now what is unit tractive force? The force exerted per unit area. So what the total area? Total area means here we are concerned about, because drag force we are talking about exerted on the perimeter of the channel. So perimeter means if we talk about the surface that over which it is being applied, so the total length will be, total surface area will be this perimeter into the length. If I talk about the channel, it is basically going like that. So this perimeter into the length, this length is same as that what I am drawing. So this is the total surface area. So tractive force say per unit area, which is nothing but the unit tractive force that we are talking about. This will be equal to, say, WALS divided by what is the surface area, that will be P into L. P into L. This is the surface area. Perimeter, length, and then L. If you open it, this is the surface area. Okay, P into L. So that we generally write as tau, tractive stress tau, or the tau is equal to, we can write, so A by P, that can be written as R. L and L would get cancelled, so this is equal to W, R and S, where W is the unit weight of water, where W is unit weight of water. What is R? We know, hydraulic radius, so I am not writing it here. And then S is bed slope. S is bed slope, and R is hydraulic radius. Okay, hydraulic radius. So we are getting that tau is equal to WRS is our relation. And now for a very wide channel, if our channel is quite wide or canal is quite wide, then as we know, for wide rectangular channel, this R can be represented with least error as depth Y. Well, so that we did discuss earlier. So this tau for wide rectangular channel, for wide rectangular channel, for wide rectangular channel, tau can be written as WY into S. So this is a very important relation and will be used for is a basic equation rather for design of channel by tractive force method. Well, now let us proceed with this idea that tau is equal to WYS. This is the shear stress. Of course, it will not be exactly equal to WYS. And what that shear stress, that is also important. Now we are having the shear force and then we are dividing it by the entire area, as if the value what we are getting is, say, equal in all the surface area. That is, we are considering that it is the average shear stress. So because shear stress actually may be different. Suppose when the water is flowing, this water is flowing through the intersection, and it is well understood that shear stress exerted at this point and maybe at this point will not be equal. That will be definitely different. But this value we are getting by dividing the total shear force by the entire surface length. And that's why we are considering this as average shear stress. And actual shear stress will of course be a little less than that and will be having some variation. So distribution. Now one more important point is average shear stress we are getting, but for design purpose we should know distribution of this shear stress, whether it will be really uniformly distributed over the surface or it will be distributed in a different way. So we are talking about distribution of shear stress. Shear stress means tractive force we are talking about, and this tractive force means again we are talking about tractive force per unit area, that is unit tractive force. Okay. So distribution of tractive force in case of wide channel is of course uniform. If we are getting a very wide channel, then as we are writing here that tau is equal to WYS, perhaps we can use this relation and we can consider that it is uniform anywhere, everywhere. But generally all channels are not that wide, and again wide means how wide, that point is there. That how much wide the channel is, that is obtained by the value of B by Y. It is always related. Say a bed width, if the bed width is 10 meter and the depth is say 0.5 meter, that also we can consider as wide. A 10 meter wide channel with suppose depth of 0.5 meter only, that can be considered as wide because B is significantly larger than depth Y. But the same 10 meter width channel, a channel with bed width 10 meter, but suppose its depth is 3 meter or 4 meter, then we cannot consider this as a wide. So wide not necessarily means only the B value. This basically means what is the B by Y ratio. B should be much larger than Y, sufficiently larger than Y. In that case only, and in that case only we can consider R to be equal to Y for wide rectangular channel. Otherwise not. R means hydraulic radius is equal to the depth that we consider when B is much larger than the Y value. So that we should be very much careful. If someone asks a question that a 20 meter wide channel, can we consider this as a wide rectangular channel? That is not the right question. we'll have to ask that if B by Y ratio is this much, can we consider this as a white rectangular channel? Well, so that part we should be careful. But for white channel, this tractive force distribution is generally when this ratio is becoming say 10 and more than that, it is becoming, we can consider this as a white channel. And for this white channel, we can consider this to be uniform. Tractive force can be considered uniform. Now, United States Bureau of Reclamation. So they studied the distribution of tractive force in trapezoidal channel, in rectangular channel, and in triangular section. In fact, they conducted a lot of experimental study, and to have this value, you do not have any other way out than to carry out experimentation. They of course conducted some other study using say numerical technique also, but their basis was experimental, and then they conducted a lot of experiment to have idea on distribution of this tractive force. And here the name of Olsen and Fleury in 1952, they are important. Of course, they are not alone. Along with them, other engineers were working, and they compiled their study as well as study conducted by other people, that all study conducted in USBR that were compiled and they gave the tractive force distribution for typical trapezoidal channels based on membrane analogy study. Based on a membrane analogy study, I do not want to go into detail of that particular study here right now, but we need to know that based on their study, they gave a distribution of tractive force. That distribution means how actually tractive stress will be varying along the perimeter. So that distribution they gave. And let us see how this distribution occurred. And of course, they did it for different type of channel, different type of trapezoidal channel. Means say trapezoidal channel with side slope something, I mean maybe 1:1.5, they conducted some experiment. With side slope 1:2, they conducted some experiment. With rectangular channel, they conducted some experiment. So like that, they conducted several experimentation. And then for all those different side slope, again they considered what is the B by Y ratio. As we were discussing, that is very, very important factor. So for say B by ratio 5, then say 10, 6, 7, for different 1, 2, even starting from 1 to 10, they conducted different experiment. And then they got those value. And let us see how these variation occur. If I am just drawing one, that is, which is available in different books also, that is for a section B by Y ratio is 4 and Z is equal to 1.5:1, 1.5 horizontal to 1 vertical. So that channel, if we draw, it is like that. Okay. So this side slope is like this. So it is 1.5 and this is 1. Well, and then this width, if the depth is, suppose depth is say y, if this depth is y, let me take little proportion to it. It is because B by Y is 1/4. So if this depth is y, then this is, say depth is y, then width is equal to 4 times of the y. This is the bed width, and this is nothing but our actually B value. B is equal to 4y. So for that particular channel, if we draw the shear stress distribution, then we can see that at the bed, the distribution is more or less uniform. It goes like this. Distribution is more or less uniform. Well, we take a different color so that it becomes more distinct. So this is the channel and the distribution is more or less uniform. say it is like that. Okay, and this maximum value of this particular distribution is obtained as 0.970 into WYS. Now what it means that every point we have shear stress. We are plotting, say graphically we are plotting the shear stress. Whatever shear stress value here we are getting, we are plotting it, and then finally we are getting the graph. This is nothing but graph of shear stress at different point. Well, at different point we are getting, say at this point the shear stress value is this much. At this point the shear stress value is this much. Like that at different point we are getting shear stress value, and then maximum value what we are getting at this point is 0.970 WYS. W means this is omega YS, unit weight of water. Fine. Now, so this distribution says that although in our analysis earlier we were getting, if we refer to this one, that is we are getting shear stress is equal to WYS. But here we are getting it as say 0.970 WYS. Of course, almost equal to WYS, but it is 0.97, almost equal to 1. So at bed we are getting. Now what about the side? Inside, shear stress distribution is not like that. Obviously, this part of soil or the surface, here the depth is less, and that's why the shear stress will also be less. But here it is increasing, and shear stress distribution is, if I plot the graph, it will be maximum somewhere here, it will be 0 here, and then here we will be having some value, and then as such the distribution will be like this. Shear stress distribution will be like this. If I plot it, plot the value like that, and the maximum will be somewhere here, and that maximum shear stress at the site, that is equal to 0.750 WYS. Writing up to say 3 decimal place, we can write like this. So there similar distribution we will be getting here also. Similar distribution we will be getting here also. So this is not uniform. This is not uniform, and that value is also say 0.750 WYS. Now, say we have some idea that how the shear stress is getting distributed on the side of the channel, and for design purpose, we are concerned about the maximum shear stress to which the channel is getting subjected. That is, if we need to make our channel safe, then we should see that at this point, this is the shear stress it is getting exerted, and on the side, this is the shear stress it is getting, it is being subjected. Now, whether we are going for this shear stress for design purpose or this shear stress, which one? Again, there is another point. That bed material, if we just imagine on the point that when the material is on the bed, the shear stress required to move this particle will be more than the shear stress required to move this particle from this particular point, because this is in rest, because it has its weight, it's a submerged condition, so it has submerged weight, it has some friction, so the force must be sufficient to move this particle by overcoming those forces. Here also it is there, but it is in the slope, so its weight particle is here, and it has a component in this direction that will also try to move it in this direction. So that way, this shear stress required for moving is also less here. And then, of course, we will be coming to that discussion in detail in our next class. But we should know one point, that the shear stress required to move this particle is less here, and that's why initially the design is started from the side slope side shear stress consideration, tractive stress consideration, and then we check whether it is safe for the bottom or not. Well, now this is what I have drawn for only one size of the channel, that is 4, where B by Y ratio is 4:1. But the channel, they conducted experiment for different time, and then for our actual design purpose also, say only with this, we cannot say that this is enough for us for our design purpose. But there may be channel, and say if we go for B by Y ratio very large, then sometimes it may not be the channel which we require, and then it may be quite large for our required section. So say depending on the discharge that need to be carried, depending on the discharge that need to be carried, our this B by Y ratio may be small. If the discharge is large, our B by Y ratio will also be large. So that way, finally, this USBR, here I am just showing the distribution, and these are all we are talking as, say this we can write as tau S maximum, so maximum shear stress at the site, and this we can write as, say, tau B max. That means out of all stress bed, it is the maximum. And then for different B by Y ratio, they gave some graphical plot for the site shear stress and for the bed shear stress. For the bed shear stress and for the site shear stress, they gave a graphical representation for all these different B by Y ratio. And just the format of the graph is like that. Say, these are popularly known as USBR curve for tractive force development, for tractive force analysis. So they plotted B by Y ratio in this x-axis, and then on the y-axis they gave unit tractive force in terms of, say, WYS. That means this value, suppose it is 0.6, it means suppose for a particular B by Y ratio 2, if we have, there will be some curve. We are not having that curve. In the next class, we will be drawing those curves, how these curves comes, and then finally we will be seeing that how these curves help us in getting the value of site tractive force, and that is suppose for a particular point, if we are getting, say, for 2 B by Y ratio, we are getting a point here, then this will indicate that the shear stress at the site will be, say, 0.6 WYS. And similarly, for, say, tractive force at the bed also, they gave a series of curves. And using those series of curves, we can have the tractive force for different size of channel, and again for different side slope. Channel may be of different B by Y ratio, as well as channel will be having different side slope. For those different side slope, different B by Y ratio, now with these curves, we will be able to have our tractive stress, unit tractive force, and then based on that value, we'll be able to design. Of course, what is required is the permissible tractive stress. What we are getting is the tractive force exerted by the flowing fluid, but we need to know that how much tractive force it can bear. That is called permissible tractive force, unit tractive force. So those we will be discussing, and based on that, how the channel can be designed by using tractive force method, design steps, that we will be discussing in the next class. Thank you very much.